Hi all. Thanks, Steve. So, yes, so we are going to do a deep dive into our latest innovation in the database portfolio, that is Aurora DSQL. So we have been discussing with our customers about their serverless architecture pattern, and when it comes to the data, oh, sorry, I forgot the clicker. Yeah. So when it comes to the data, they actually don't have a solution that is something like DynamoDB in the relational database space. And we have customers who actually look for active configuration to build always available applications to serve the customers in and across the regions as well. That's why we introduced Amazon Aurora DSQL, which is a distributed SQL database in the last reinvent. My name is Arun Sankaranarayan. I'm a database specialist solution architect. I'm based in the UK. And I'll be having Divya, who will be co-presenting with me. Like I said, let's have a look into the challenges that the relational databases were having, the customers were facing. If you look at it, with the traditional relational databases, scalability was a big challenge. Customers often hit the capacity limit, and they will end up doing right sizing or migrating to a different system or refactoring the system. And unplanned downtime is another challenge. With the lower resiliency rate of these traditional relational databases, customer has to face unplanned downtime, which affect the business of the mission critical applications and which negatively impact the revenue and profitability of the organizations. Apart from the unplanned downtime, customers have to plan for their infrastructure and database patching and upgrade, which also need to bring the system down. And this is also causing problem to their business. Complexity is another challenge where you have to install your database, you have to configure it, you have to do the setup, you need to manage and operate it. We were able to solve these challenges with Amazon Relational Database Service. RDS is a fully managed database service where AWS is taking care of all the heavy lifting activities on behalf of our customers. We took a step further by introducing Amazon Aurora, which was a major departure from the traditional database design. Now we have Aurora Serverless and Aurora Limitless, where it is removing the need of provisioning your infrastructure upfront by giving on-demand scaling with your workload. Today we have Amazon Aurora into the Amazon Aurora DSQL into the Aurora family. Aurora DSQL is a cloud-native serverless distributed SQL database that provides unlimited scaling, eliminates the need of infrastructure management, and delivers highest availability by ensuring that your data is strongly consistent. When I say unlimited scaling, Aurora DSQL follows a disaggregated component architecture. The components like compute, read, write, and storage can scale independently, horizontally, dynamically with your workload. DSQL, which means you don't need to worry about your capacity limit. And with DSQL, you will be getting 5 nines of availability. With its active distributed architecture, you will be able to build always available applications to serve your customers in and across the region. DSQL is truly serverless. There are no servers to patch, provision, or you don't need to install any softwares, or you don't even need to worry about managing and operating the database instance. And this is also eliminating the need of bringing down your system for patching and upgrade. DSQL is fast and easy to use. Within few minutes, you can create the cluster and start querying your database. For developers, you will be using very familiar PostgreSQL database engine. DSQL is compatible with PostgreSQL. We have used certain components of the PostgreSQL in DSQL, which includes PostgreSQL via protocol, drivers, dialect, and type system, and core features like ACID transactions, secondary indexes, joins, and schema. So what it means to you? For you, you don't need to worry about rewriting your queries. You can continue use your SQL queries in DSQL. There are some features which are not supported at the moment in DSQL, so you might need to do some refactoring when migrating to DSQL. You can create DSQL in single region and multi-region clusters. If you look into the single region cluster, which operate actively across 3 availability zones. When you think about read transactions or even read-write transaction in a single region cluster, it happens locally. The transaction has to do a cross AC communication only during the time of commit to make sure that your transaction is durable, isolated, and atomic. Now let's say a component or the AC impaired in a single region cluster. DSQL will be directing into the healthy components, and the impaired component will be fixed asynchronously in the background. Once it is fixed, it will be added back to the cluster. So with DSQL, you will be getting 4 nines of availability. Multi-region clusters provides the same resilience and connectivity as single region clusters while improving the availability through 2 regional endpoints. You will be getting 2 regional endpoints which could act as single logical databases by providing concurrent read and write operations. There are no primary secondary concept in Aurora DSQL, which means both regions are equal peers. Now when we look into a read transaction, all the read operations are local because you have the strongly consistent data in each region. When we look into the read-write transaction, most of the transaction happening locally, but it has to do a cross-region communication to make sure that there are no conflicts. Here we have a third region called as witness region. So witness region is responsible to keep your encrypted transaction logs for a short period of time. Witness region will not be having the full database copy, so you will not be getting an endpoint to connect to the witness region. Now let's take a scenario of a region failure. Let's say the region on the right-hand side failed. You still have the 2 regions available. So you will be able to route the connections to the healthy region, and the witness region take part in the quorum to continue the transaction or to give the strong consistency. With this, you will be getting 5 nines of availability with 0 data loss. Now let's have a look into the components, internal components of DSQL. Like you will be having a front end that your client will be connecting to the DSQL, and each connection in DSQL will be getting a query processor. Query processor is heart of the DSQL, which is responsible for executing your SQL and returning data in response to your reads, buffering data in response to your writes. Then you have adjudicator. So adjudicator plays a crucial role in a read-write transaction. Adjudicator actually look for the conflicts based on some isolation rules to decide whether your transactions can be committed or not. Then you have journals. Journals are ordered data streams that makes your transactions durable. So we have been using journals in AWS since a decade for different services. If you look into traditional database design, your transaction is considered as durable only once it reaches into the storage. But here, once the data committed and comes to the journal, your transaction is durable. And journals are responsible for replicating your data in the AC and across the regions. Then you have crossbar. So crossbars are responsible to check the ordered data streams are sent to the storage nodes sequentially. Then you have the storage nodes where you will be able to read the data from table and indexes. Now let's have a look into an example of a read transaction. Let's see how a read transaction works in DSQL. Here we can take a situation where customer want to find top rated restaurant using a food delivery app. The customer choose the ratings and try to find the restaurant. What is happening at the back end? It's a select query for us, right? It's a select query that being run. It's a read operation. So how it will be working in DSQL? So the client will be connecting to the front end of DSQL, and each connection will be getting a query processor, like I mentioned. So this connection will be getting a query processor. Now this transaction has to find the transaction start time, which is with the help of the local clock. So here we have used Amazon time sync service to help in this situation. So now you have the transaction start time. What is happening next? Now the query processor will look into the shard map and identify in which storage shard we have the data that the customer is looking for. Then the request will be directly sent to the storage shard. So here I would like to highlight one thing. We can see other components of DSQL here, but the read transaction is not communicating with other components. So in DSQL, read path and write path are different. What is happening next? We return the result from the storage nodes. So this data will be returned to the query processor. And here I would like to highlight another thing. I mentioned about a transaction start time. In DSQL, you will be having when you start a transaction, you will be having a transaction start time. Let's say it's T start. You will be able to see the data as of your transaction start time, which means there will be other transaction happening at the same time as yours, or other transactions started after yours, which is not conflicting with your transaction. This is basically with the help of multi-version concurrency control at the storage tier. So we have the data read from the storage node, and this will be sent back to the client. Now the user will be able to see what are the top rated restaurant in the area that they are looking for. Now let's look into the interactive transactions. I would like to hand over to Divya to dive deep into the interactive transaction.
Thanks, Arun. That was great. My name is Divya, and before diving deep into this, I am a RDS Postgres Specialist SA based in Ireland. And we are also joined by the two of us by James, who actually helped me understand this architecture very well. And also Sharma, who is the director of DSQL, who was in a very interesting roundtable yesterday when we did have some questions about the core architecture of DSQL. So if you have any questions, we'll only be able to take them later after this, but it's the four of us, so as many questions as you have. So let's get into a more complicated piece where all the architecture components come into play, which is an interactive transaction. So now you have the list of restaurants, right? But you want to order a pizza. That's what I did yesterday. So now with the top rated restaurants, I pick when you send your order, you basically select a particular restaurant, you select a particular item, the restaurant would update that item, reduce a quantity, and store order and user information, right? That type of a transaction is read, modify, and write. It's not just a read transaction. We are doing some changes and we are writing it there. But now let's see how this goes into DSQL. How does this work? So the query processor is like a holding tank for your statements. So we are not sending anything to the next layer or to the cross region even until you commit. So as I said, it's like a holding tank. It's waiting for the transaction, doing all the processing inside this box till the time the commit happens. And this is a Firecracker micro VM. This query processor, it runs inside a Firecracker micro VM, which is not new. It's a service we've launched for Lambda before, And it's basically small virtual machines which are very fast to process small amounts of data. So this is what is a very major component of DSQL where the processing is taking place. What's actually happening inside this query processor is, as you can see, it is basically taking a snap, sorry, I think it moved a bit too quickly. Just a second. Yes, this is the first step. DSQL follows snapshot isolation, which means each transaction operates on a snapshot which it took at the T start, the start time, right? So all the changes which are happening are on the snapshot, and you are making those changes which are visible, of course, to your transaction, right? That's the isolation you get here. Now, as I said, it is processing it locally till the time you commit. So it spools the writes locally on the query processing layer. That means taking the rows you are acting on, doing the changes you wish to do to those rows or that set of data, and then having a post image of that. But if we are allowed to commit or not, I'm not sure yet, because there might be a conflict. There might be some other transaction which started to modify the same data after my transaction started. And that's a problem, because if that transaction commits first, my snapshot or my version of data is invalid, right? So because of the changes if I'm trying to do. So we have to do a cross-region interaction only at commit time. So all the other processing was happening inside the query processor. After that, we look into how we are checking this. In DSQL, we are using optimistic concurrency control, which, as I explained, we are taking a snapshot, making those changes, and checks validation at commit time. And now let's see if that validation, who is doing that validation check, if the commit would proceed. And that component is called the adjudicator. This is for that check of conflict. If transaction A and transaction B start at certain times, which one will be allowed to commit? If they are modifying the same set of rows, if they are modifying different data, we will see in certain examples. But it sits in the right path of the DSQL and is used to detect and resolve conflicts. What happens now? So the query processor sends a payload to the adjudicator. And what this payload consists of is the T start, which is the start time of the transaction, the write set, the rows or the data set which this transaction which is to modify, and the post image. What happens when I have made these changes? I have processed the transaction, and this is the post image. This is how the data will look like after. And this payload is sent from the query processor to the adjudicator. Now this is the core of the adjudicator algorithm. It's pretty simple to understand. It's basically what I just said earlier, that here are the keys I intend to write. So this is exactly what I want to write, and this is my T start, right? This is the start time of the transaction. If no other transaction has written these keys since T start, that means if nobody has actually invalidated my snapshot, because if somebody has changed that, we lose consistency, right? I cannot write anymore. Then, if nobody has started a conflicting write, pick a commit time and write these changes to the journal. That's the other part we'll get to. But basically, pick a commit time and make the data durable. The adjudicator is saying, I'm also not allowing another transaction to pick a lower T commit, which kind of means the same thing. If another transaction commits before this one, that again means that the data I'm seeing has been invalidated. So no transaction gets to pick a lower T commit, and nothing has started before the time I was seeing this data. And let's check this with an example. So we have two concurrent transactions, transaction A and transaction B. The transaction A has started 10:9:33 and the other one has started 10:9:35. This is 2 seconds after that, after transaction A, but what is the deciding factor is which one commits first. So in this example, I am telling you that transaction A committed first, right? And the other important thing is they both are acting on the same data. So if you see ID is equal to 3 on both sides, so they are acting on the same set of rows. Because of that, these writes were conflicting. And because transaction A committed first, we know that, okay, transaction A is allowed to proceed. However, B will be aborted and there has to be some retry logic for B, right? So you'll have to retry that transaction. If the commit is conflicting, but it's acting on a different set of keys, this is item ID 3 and this is item ID 7, there is no conflict. So because of that, they both are allowed to proceed and both of the transactions are allowed to commit. We said there that if it's allowed to commit, go ahead, give it a T commit and write it to the journal. In DSQL, the durability is handled by the journal. In a traditional architecture, this durability is handled by the storage, but in DSQL, that is handled by the journal. The journal is basically, you can consider it as a log of all the transactions, all the changes which are happening, which is responsible for the durability of whatever I have written. So once this happens, once it's written to the journal, it's committed, it's durable, and there can be many journals. So the benefit of this architecture is that all the components scale independently, right? Journals can scale independently, adjudicators scale independently, the storage, of course, can scale independently. And so because of that, there can be multiple journals, but the sequence is important. How those changes happen, the sequencing of those journals, that to ensure that all of them that goes in a sequence to the storage is handled by this crossbar component. And finally, it's written to the storage, right? So this is the entire architecture. The query processor sends a payload to the adjudicator. Adjudicator once decides which is allowed to proceed or commit, writes it to the journal then sequenced and then written, maintaining the sequence written to the storage, right? Simple enough. Let's look at the active-active architecture, right? DSQL provides multi-region active-active with the same architecture which we discussed as to how a query processes, but let's look at how it scales. So in this diagram, we have 3 regions, A, B, and C. We have all the components we just described. There is one thing to notice, the adjudicators are split. So the reason, I think I didn't explain it just yet, why we need cross-region collaboration when there is a commit. Because if you look at this, the keys are split between adjudicators. So there is a basically leader adjudicator for certain set of keys. And in this example, A to M is the keys, the leader is the this adjudicator, and for N to Z, it's this one. Because of this, when I'm committing, I need to check cross-region, right? So to be able to make sure that there is nothing conflicting. And the adjudicators are obviously writing to the journals, and the storage is split across. You have a consistent copy across all the regions, right? The journal part is also important for this replication of data from region A to region C, region B being the witness region, so that if region C fails, the data is still durable within the journal, and that journal can still can be a part of the quorum and maintain that availability. While in the last part, we had the adjudicator here, But now because there is a partition, this region has failed. I have to move those keys towards the available region. One another thing which we didn't notice, which we didn't mention earlier as well, there are two regional endpoints in this case. One is the regional endpoint for region A, and one is for region C. You will, once this, if this scenario happens of a failure here, you will still be able to connect and do all your operations and transactions through region A. Right, it will be available, and because of course of the journal and the scalable architecture, you will get that scale. We highlighted that as well, that DSQL follows the optimistic concurrency control, because of which there is no locking overhead, there are no deadlocks, and transactions do not block each other. There is no concept of blocks or taking locks on tables and for transactions. Local processing of the queries or of the transactions, because the query processor was only going to the other region when at commit time, right? Efficient synchronous replication because of the journal, which is also responsible for making the data durable. And Aurora DSQL's optimistic concurrency control basically helps to efficiently scale this system. But in case there are aborts for transactions, as I said earlier, transaction B will abort, you will have to have a mechanism in our application for retries. That's all from our side. Thank you so much. And these are some of the useful links for further study. And if you have any questions, we are happy to take them. Thanks.